So we had stopped right before symmetry. Yeah, this was the last example we did. So this is where we need to get started. It's warming up. Yeah, it takes it a while. Okay, so trying to finish 2.3 and 2.4 today. 2.4, as you can see, is a pretty small handout. Okay, so transformations, we're done with that. Now we're getting into symmetry. So the two types of symmetry we will be talking about is with respect to the y-axis. So the idea is if you were to fold your graph along the y-axis, your two halves should coincide evenly with each other, right? In other terms, you can actually think in terms of distances. So if I take a distance from the y-axis to this point, negative 2, 4, and I take the distance again from the y-axis to positive 2, 4, this distance has to be the same. And of course, the same thing with these 2 points here at the bottom. And as you can see, this is our parabola, right? Y equals x squared graph. So parabolas will have symmetry with respect to the y-axis. But if we do those horizontal translations, right, where we move our graph to the right or left, then your line of symmetry, which is what we call as axis of symmetry, will change. But parabolas will have symmetry. Now, they also actually talk about symmetry with respect to the x-axis, but we're not really going to be looking at symmetry with x-axis, but the idea is still the same thing. So you've got your positive x squared function on the top. So that's a parabola opening up. And we've got its reflection. So that's a negative x squared function here on the bottom. So with respect to the x-axis, if we look at this distance from the x-axis to negative 2, 4, and from x-axis to negative 2, negative 4, then same thing, this distance has to be the same, and same thing on the right-hand side. But like I said, we're not really talking about symmetry with respect to the x-axis, so we'll do symmetry with respect to y-axis. And we also talk about symmetry with respect to the origin. So with the origin, since origin is just a point, right, 0, 0, you can't really talk about folding it and having your two halves coincide. So we talk about symmetry with the origin in terms of distances. So with a graph like this, which is y equals x to the third power, or the cube function, if you take the distance from the origin to the point 2, 8, and the distance from the origin to the point negative 2, negative 8, again, that distance has to be the same. And if you can show that, then that means you have symmetry with respect to the origin. So the two different types of functions we're looking at, symmetry with the y-axis, that happens with even functions, and all even functions will have symmetry about the y-axis. If you look at symmetry about the origin, then that's going to be for all the odd functions, and all odd functions have symmetry with respect to the origin. Now, you know, obviously every time we're not going to want to try and graph these to see what kind of symmetry they have. And, you know, for most part, once you start getting into higher degree functions, your graphs are not going to be very accurate. Your graphs are not going to show you all the details. So we don't actually really depend graphically to try and show if you have an odd function or an even function and what kind of symmetry it has. So we actually use little algebra to help us out. So right here you will see we're talking about if you take your original function which is given to you, so f of x equals x squared, f of x equals x to the third power, whatever that original function will be, replace the x with a negative x. So you're basically bringing in a negative x for all your original x values, and then you try to see if I bring in a negative x, do I actually go back to the original function? So if your signs don't change, none of the original function changes, it stays the same. That's when we can say we have an even function. And like I said, all even functions have symmetry about the y-axis. If you do that same kind of algebraic calculation and put a negative x into the function, but it actually makes the whole function negative, so it will change, right? Instead of keeping it the original, if your whole original function becomes a negative of what you had, that means you actually have an odd function, and all odd functions have symmetry about the origin. Okay, so that's actually the idea behind looking for symmetry, is putting in this negative x in your original function and then seeing, am I getting the original function? If I do, it's even. Y-axis is my symmetry. If it makes my original function a negative on the entire thing, then I have an odd function, which means I have symmetry about the origin. So something you should keep in mind when you're doing these little tests with the negative x is what happens when I put a negative x on something that has an exponent on it. So for that first part, they are saying if n is a negative number, so think about it this way. If you have negative x to the third power, right? So n is a odd number. So think about it. It's negative x multiplied into itself 3 times. What will you end up getting? Negative? I'm looking for what's after negative. Yeah, you're going to get negative x to the third. So this is what they're talking about. If you have negative x inside and an exponent, which is an odd number, so 3, 5, 7, you know, any of those exponents, you're actually going to have a negative sign left behind. But if I do the same calculation with negative x to the fourth power, so an even number, you're basically adding one more negative x than we did in the previous one. Yeah, because 2 negatives become positive, right? And they will have pairs here. So your 2 negatives become positive, 2 negatives become positive, giving you a positive x to the fourth. So they are saying if you have a negative x to the nth power, where n is an even number, that negative sign does not stay behind, right? It all becomes positive. So that's something we're going to need when we're doing these calculations. You can see these are the same values we used here. So for number 10, if you take your function and replace all the x values, bless you, with negative x. So that will make it negative x, parentheses, 4 on the outside, so fourth power, minus, and then again, negative x in parentheses to the third power. So you're taking wherever you see an x, replace it with negative x. This negative is staying as it is, okay, from the formula or the function itself. Now we just saw negative x to the fourth power will end up becoming a positive x to the fourth, right? So this first part, and I think I'm actually going to write it down here, will become a positive x to the fourth. Keep this negative sign in the middle as it is. So this guy, just bring it down. And then our negative x to the third power is where we had that negative sign left behind, right? So you're actually going to have another negative sign and x to the third. So what happens with 2 negatives? They will become positive. Yeah, so you will end up with x to the fourth plus x to the third. Now, if this was an even function, we should have gone back to the original function you started out with. Now, do these look the same? No, right? So that means we don't have an even function. Okay. So this is not an even function. You have to make sure it is. Just because it's even does not automatically make it odd. So be careful about that. So for it to be odd, remember what I said, it should make the entire function negative, right? So the idea here is what happens if I put a negative sign in front of my function. So if you do negative on the outside, that means you're taking negative of x to the fourth minus x to the third, which was our original function. So will we get a negative of the original function? Because if you distribute this negative sign, you will have negative x to the fourth, negative and negative, positive x to the third, right? Is that the same as this guy? Oh, no, it's not. What are we missing? Negative. Very nice. That's what I wanted you to see. Yeah, so you have positive x to the fourth, positive x to the third, but when I make my entire function negative, the first term should become negative, right? So these guys are not the same. So this is not odd or even. So it's actually both has been denied. So it's not an even function. It's not an odd function.
So it's not even it's not symmetrical at all.
So there's no symmetry on this function, yeah. Now some functions bring their own symmetry, but this guy actually is not going to be. And let me actually show you what the graph looks like on our little Desmos calculator. So this guy will be x to the 4th minus x to the 3rd. Yeah, and look at that. So you're not really seeing, because if we fold along the y-axis, it's not going to be equal halves, right? And if we talk about distance from the origin, there's really no distance from the origin either. Yeah, so this guy is not going to have any symmetry. But like I said, we don't really want to depend on just, oh, where are you? Just the graph to help us out. So when you do it algebraically like we did here, then you have a concrete answer. Any questions at this point? And I will actually point something out after we've gone through the other examples and show you an easier way to also kind of judge this.
The not an odd function, is it for this set or that set? Or is it for the same one?
So since I did not get this same thing here, that's what's making it a not odd function. And since I did not come back to the original function I started out with, that's why it's not an even function.
So the first test will always test to see if it's
Even,
no
yeah,
matter what.
yeah, exactly.
And then from testing your new one,
Yeah, by putting a negative in front of the original function, then you can see if it's going to be odd or not.
if it was odd, it would equal what the first equation came out.
It wouldn't equal. This is just a test to see, is it an even function? Is it an odd function? So it wouldn't equal, because equal would be you have to get the same thing, right? But if it was an odd function, that means you have a negative on the entire function. So that means both your signs would have to change.
Similar to what the original was.
Yeah, so if both your signs did change when we did this little calculation, then I could have said it is an odd function. So basically what you're doing, you take your original function, put that negative x in, right? Which is what we did in this part. And we came up with x to the 4th plus x to the 3rd. So now we know, obviously, it's not the same function I started out with. So that's my first test, which means he's not an even function. Because if you come back to the original as it is, if I got x to the 4th minus x to the 3rd here, I would have said these guys are even. This is an even function, which means it will have symmetry with the y-axis, but I didn't come with that. Now, how do I know if it's an odd function or not? So to test, to see if it's an odd function, this is what we did here. Took our original function and put a negative sign in front of it, and then, distribute that negative sign. If these two would have matched, if they came to be exactly the same, then I could say, yes, it's an odd function. It has symmetry with respect to the origin. But again, since these guys are not the same either, it's not an odd function. So you're testing to see if it's going to be one or the other. Okay? Anybody else? Any question on this? Okay, so let's try this again for number 11 here. For number 11, same thing. Take your original function, replace the x with negative x. So everywhere you see an x, replace it with negative x. And since there's no other numbers that I can multiply or do anything, basically this guy is now becoming minus x. Is it the same as the original function? No, which means this is not an even function. Is it an odd function? So for that, all you have to do is take the original function and put a negative sign in front of it. So if I take the original function and put a negative sign in front of it, it gives me this negative x, right? So since these come out to be the same, it's an odd function. odd functions have symmetry about the origin. And the easiest way to remember is both odd and origin begin with O's. So they go together, so O and O, okay? Which would leave them even with the y-axis. Question on this guy? All right, let's check 12, which is absolute value of x squared minus 3. So if I put in negative x for my x value, what am I going to get? Beatrice? Okay, so think about this. And you know, there's a reason why I'm always putting my negative x in parentheses, so you remember that's the value replacing your original x. So if I have negative x to the second power, you can actually go back and look at these rules. So if it's an even exponent, what happens to your x? It becomes positive, yeah. So that's what you're going to use here, which means the negative x to the second power will actually end up becoming positive x squared minus 3. So does it match the original function you started out with? Yeah, so you don't even have to worry about checking for an odd because it came back to the original function, which means it's an even function, and even functions have symmetry. Very good. And you know, this is an absolute value function. You can see those little symbols. So if you look at the graph for this guy, so absolute value of x squared, nope, minus 3.
So it'd be symmetrical across the y-axis?
Yes, for the x squared minus 3, and this is what your graph ends up looking like. So you can see if we were to fold right along the y-axis, our two halves would coincide, bless you, or you can think in terms of distance, right? So if I take the distance from, let's say, this point to this point here, and then from this point to this point, it's going to be equal distance. You can think of it that way, or with y-axis, you can just fold along the y-axis and see if your two halves coincide, which this guy does. And we just proved that algebraically when we put our little negative x in and still came back with the original. Oh, all righty. What do you think will happen with function x plus 3, the whole quantity squared? So start out with, again, replacing x with negative x. And if you want to put that in parentheses, you can actually use brackets for the outside, negative x in parentheses, plus 3 squared. So however you want to write it down. So this one is kind of hard to tell, right? The way it's set up. But anybody has a clue at this point? You can try that, yeah. So let's start by actually doing a FOIL on the original function. So if you did x plus 3 squared, and you try to FOIL that, what will we get?
X squared plus 6x plus 9.
Very nice, exactly. Okay, I'm gonna have to redo this guy. Yes, if we make each x negative in that, so that will basically become negative x squared plus 6 times negative x plus 9 So again, the negative x squared is to an even exponent, so he will become positive. So that's positive x squared. Here, you're multiplying positive 6 with negative 6, so positive times negative is negative. So did we come back to the original? No. So it's not an even function. Now to check and see if it's a odd function, you take your original and put a negative in front of it, right? So I'm actually going to show that. Here, if I put a negative in front of the original function, and I'm going to use the FOIL version here, that should give us negative x squared, negative 6x, negative 9. Do these two match? No, because it's only the 6x that has the negative, but the others don't. So that means this little test we just did tells us it's not an odd function either. So does that mean we have no symmetry?
There's symmetry.
Say that one more time?
There is symmetry.
Okay, do you know where that symmetry is?
0.30 or negative 3. Yeah, negative
Ding,
30.
ding, ding. So this is actually a unique function, and you're about to find out why he's unique. Come on, buddy. So parentheses, x squared plus 3, right? Plus, where are you? No, I did that wrong. It's x plus 3 squared on the outside. There we go. So what are we seeing when we graph this function? What's that shape? Parabola. And you can see right here, instead of being at the y-axis, your axis of symmetry has actually moved 3 units, right? So if we didn't have that plus 3 with our x, you would have been right here at the starting point origin y-axis. But since we moved 3 units left, your axis of symmetry has actually also moved 3 units left. So you are going to see, one second, you are going to see 2 different types of questions for this. One, which I'm suspecting this one might be that, where they might actually just give you the option of symmetry at the y-axis, symmetry at the origin, or no symmetry. If that's the case, you would say no symmetry. But if they ask you specifically, now I kind of wish I had done this on the other piece of paper, but either you will say no symmetry, or you will say symmetry is at x equals negative 3. And why is it negative? Because remember, with horizontal movements, we go with opposite signs. So since this is moving 3 units to the left, that's the negative 3. So parabolas may not be an odd or even function like we saw in this example, but they can, because it's a parabola, bring their own symmetry to the play. Okay, so this would be the only exception where it may not be odd or even, but then, you know, like I said, the parabola is bringing its own symmetry. So there will be 2 different types of questions. One, where you may just have to select the bullet point which says no symmetry and be done with it. But then some of them will give you the option of symmetric about, and it will give you x equals and then the little blank space where you would type in the line where it's symmetry at, and that's where you would type in the negative 3. So I'm going to show you both answers, so that way whichever example you see first, you're ready to put the answers in. Okay, so does it make sense why our symmetry is not at the y-axis but at negative 3? Yeah, because of that graph making a horizontal movement 3 units to the left. Okay. All right, guys.
What if it said x is minus 3 squared? Would that bring it over to the right?
Yes, so if it was x minus 3 and then the square on the outside, you would be at the right. which means this guy would then be positive. Yeah, very good. Okay, so I was talking about there's a shortcut way of knowing if you have an odd or an even function, and that's actually kind of what they're talking about in this little paragraph here. So, bless you. They're talking about you can either have just a x squared function like this, which that exponent is an even number, right? So an x squared function, because it has an even exponent, is actually an even function, which means symmetry with respect to the y-axis. Bless you. Wow, what is going on with you people? I'm going to have to ban all of you from coming to class. Don't even say that. My mom is so freaked out. We're not allowed to go anywhere. She's like, we're not going on spring break. We're going to stay home. So yeah, please don't freak her out. She's already telling me to wear a mask everywhere I go. And I was like, I can't teach in a mask. So, exactly. Okay, so just a single x squared, or look at all the exponents on this guy. So we have x to the 6th, even number, x to the 4th, again, even number, x squared, even number. And this guy, technically, we actually think of him as being 3 times x to the 0 instead of just a constant 3. And in this case, we're actually bringing the 0 to the even side, and we're saying 0 is an even number. So since all my exponents here are even, this is actually an even function, which means he will have symmetry with respect to the y-axis. In that same way, think about the function x to the 3rd. 3 is an odd number, which means this is your odd function, symmetry with respect to the origin. And then something like this also, where you have x to the 5th, odd number, x to the 3rd, odd number, and this is x to the 1st power, which is again an odd number. So if you have something like this, that's an odd function, symmetry with respect to the origin. But if I mix both the powers together, and that's kind of what, that's kind of what we have here, even and odd, right? X to the 2nd power is even, x to the 1st power is odd. So when it's a combination of both odd and even exponents, you will have no symmetry. I mean, neither of these at least. You will not have origin or the y-axis as your symmetry. Now this guy is again an x squared function, which makes him a quadratic function, which is a parabola, so he can actually bring his own symmetry. No, so this guy actually is, you're only looking at this part of the function, so you don't have the +9. So that actually means you don't have that +3. So this one we would actually need to do a little bit of math to find out where it's going to be. I think it ends up being, I think it's going to be like a fraction 3/2 or something like that is what it comes out to be. So yeah, this is going to be not at a whole number or integer for that matter. So if you go back and look at our 4 examples that we did, let's start with that first one. So this guy here was a combination of both even and odd powers, right? X to the 4th and x to the 3rd. And you can see that's why it didn't classify as odd or an even function. So since it had both exponents in there, this was neither symmetry, basically. This guy here is just x to the 1st power, right? So that's an odd number. You had an odd function, symmetry at the origin. Now this guy is actually, you can still use that idea of odd or even exponents, since this is x to the 2nd power, which is even. You can think of 3 as being x to the 0 power, which is again even. But you know, absolute value functions like parabolas also bring symmetry just because of that V shape that you have. And then that square, remember, was giving us that little dome in the middle. So that's actually what's making it an even function. Sorry, I lost my train of thought. And then the last one, if you look at the foiled version, right? Because here it's kind of hard to tell, but this is a combination of even, odd, and even powers. So since it's a combination of odd and even, you're not going to see symmetry at the y-axis or the origin, but being a parabola, he's bringing his own symmetry. Okay? So you just kind of have to look at what kind of examples you have and then kind of see what it looks like. Now, I was talking about symmetry with respect to the x-axis, the reason we cannot use symmetry with respect to the x-axis is because, think about how we had defined functions. If you draw a vertical line through a function, it should only cross at one point. But then if you talk about symmetry with respect to the x-axis right here, think about if I drew a vertical line here, it would be crossing at 2 points, which would fail to become a function. And since we're only working with functions, that's why we're not talking about symmetry with respect to the x-axis. Okay? But that's kind of what happens with
Will that
this
come
guy.
up later?
Not for our class, it will not. Because mainly we will be working with functions. And even if we are not working with functions, the relations we're going to be looking at, we're not going to be talking about them in terms of symmetry. So for our class, we're only doing the y-axis symmetry and the origin. Okay, very good. Any other questions? Okay. Our last part here is actually talking about using graphs to help us come up with these solutions for the inequality. So they're saying solving each inequality by graphing the appropriate function and then state the result or your solution set in interval notation. So the first thing we're actually going to do is take this expression part and set it equal to y and graph that function. So just take that first part, set it equal to y, and you can do table, you can use transformations, so it's actually up to you. Can anybody tell me, if we were doing transformation, what's our base function here? Very nice. Your base function is x squared, and what kind of movements are we doing by bringing these numbers in? What's the -1 telling us? Very good. It is going to the right 1 unit. And that -9? Very good. Going down by 9 units. So you can use that to help you come up with the graph. Or like I said, if you want to do a table, you can use a table. I think I actually used transformations, if I remember correctly. Okay, so let's see. This guy was originally less than 0, so we're saying y equals x minus 1 squared minus 9, right 1, down 9. Okay. Whoa. What happened here?
Very thick purple.
Yeah, where did that come from? Not what I want. Okay, there we go. Okay. Now, if you were using transformations, your original table would look something like this. -2 squared would be 4, -1 squared would be 1, 0 would be 0. So we are moving 1 unit to the right and 9 units down. So if you wanted to use transformations from all the x values with 1 unit right, what do we do? Add or subtract? add. So for each x value, you would be adding. And you know, you can verify that. Think about what happens if I put -2 in for my x in this function, what value am I getting? And eventually you will see what happens when you've added 1 to each of those. So -2 plus 1 would put us at -1. -1 plus 1, 0. 1 plus 1 would be 2. 2 plus 1 would be 3. We're probably going to need more points in here. And I need, yeah, negative side also. So probably need to bring in -2, -3, maybe even -4. Okay. And then from all the original y values, we would be adding or subtracting 9? Subtracting, yeah. So you would do 4 minus 9. 1 minus 9, bless you. 0 minus 9. 1 minus. Oh, I lost my thought again. Bless you. Allergic to math? Is that what's happening?
I think so.
You think so? Oh, I missed a point in there, didn't I? Sorry, I missed a number in there. That should be -1, 0, 1, 2, and 3. Yeah, so to all the x values, we added 1. To all the y values, we subtracted 9 from the original table. And then these are extra points if you need them, which you will. So -1 should be at -5. 0 should be at -8. 1 should be at -9. 2 should be at -8. 3 should be at -5. I need 2 more points that tell me where I'm going to be crossing my x-axis at. How can I find that?
You follow the trend?
Sorry?
Did you follow the trend?
Follow the trend?
Yeah.
You could, but I'm not going to do that because I know my graph is not accurate. You guys may have better luck. Where are we crossing the x-axis at? And how do we find that? Other than what Brian said about following the graph. This is what you guys were supposed to do on your lab handout. How do we find? Yeah, to find where your graph is going to be crossing the x-axis at means you are trying to find your x-intercepts. To find your x-intercepts, make your y value 0. Yeah, so you would have 0 equals x minus 1 squared minus 9. Uh-huh.
So on our test, are we supposed to be breaking down each individual section of it? 'Cause I just went right to the final and the final.
What do you mean by breaking it down to each individual section?
Like, in this case, we did y equals x squared. So
Oh, that was just, I was telling you, if you were using transformation to graph, you can go directly by creating a table for the original function, which is the x minus 1 squared. Yeah, so if you're not using transformation, go directly to finding points for the final function. Yeah.
would it be beneficial to not do it that way?
You know, it's really a preference thing, so I would be okay with whichever method you go with. So what you're comfortable with, if you don't want to do transformation and just go directly to the graph, go ahead and do that. Yeah, not a problem. Okay, So if you are trying to find your x-intercepts, and that will honestly be something we need to solve this problem. So take your y, replace it with a 0, and now try to isolate your x variable. So that would be starting by adding the 9 first to both sides. You will be left behind with 9 equals x minus 1 squared. Now you guys did this in chapter 1 when we were solving using the square root property. So what do we do at this stage? No. Yes, you have to take the square root to get rid of the square on that right-hand side. So be careful. FOIL is what Jacob said. I guess you could do that, but that would, to me, it seems like a longer way to go about, but you could do FOIL and then use factoring to simplify if you wanted to try it that way. It will work. Because that's the beauty of quadratics, is you can use a bunch of different methods and still work. Okay, so square root, please remember every time you take a square root, you get one positive, one negative root. So the square root will cancel out the square, leaving us behind with positive and negative 3 on the left. And since the square is gone, you can actually just write it as x minus 1. And the very last thing we do, very nice, add the 1 to both sides. So you will do plus 3 plus 1 and then minus 3 plus 1, right? Which will give us positive 4, and what's the other one? Negative 2. So those will be our x-intercepts, 4, 0 and negative 2, 0. Is that what you guys got when you did your graphs? Yeah? Okay, so positive 4, 0, negative 2, 0. Let's see, positive 4, negative 2. So now, yeah, very good. Yeah, if you have a grid, then you should be able to follow that path like you were talking about. But I know since I'm doing this freehand, my graph's going to be all over. So I prefer to have numbers to help me out. Okay, now you guys are lucky because my math lab will give you the graph. So you don't actually have to draw it. Hush. You've got good eyes. You don't have to worry about reading glasses every time you leave your office. So now the question is, this expression, which is what we're calling y, has to be less than 0, which means you're basically saying, where is your graph going to be where your y values are less than 0? So looking at that graph, what interval notation can we use where our y values will be less than 0?
Negative 9 to
I wish I could say that was right.
I didn't say it's right. You can say it.
I can't, it's not right.
You are right.
Interval, interval notation. What values do we use for interval notation? Yes, but still the question stands. What values do we use for interval notation?
0, 9, or no.
No, negative 9 is definitely not part of our answer. Nope.
Parentheses, negative 8.
Thank you. Interval notation is always going to use the x values, even though we are talking about where the y is negative, we are still talking in interval notation. You have to put the x values for which the y will be less than 0. Yes. Now, what kind of symbols do you put on negative 2 and 4? No.
Parentheses.
Parentheses, because this is a strictly less than. If it was less than with the equal to sign, that's when the brackets come in. So they are basically saying your y value cannot be equal to 0, it can be less than 0. So it can be negative, but not 0, right? So look at the graph. Right here on the x-axis, y values are all equal to 0, right? The moment you drop below it, your y values start becoming negative. Above it, it's positive. So when they're saying this guy has to be less than 0, that means they're saying all of these values, which would be actually everything that falls on this part of our graph, right? All the points here. And interval notation always uses x values. So that's why it's going to be between -2 from here to 4 in here, but not including the endpoints because we have a strictly less than inequality. So your solution set is between -2 and 4, not including the endpoints.